In this section we will talk in detail about the sample conditioning equipment. Sample conditioning is the process of filtration of the sample, adjusting the pressure and flow of the sample, cooling or heating the sample to the appropriate temperature. The first equipment we are going to talk about is the Advanced Reflux Sampler. This equipment is installed directly at the process nozzle before the sample line. It is used for primary conditioning at the sample tap. Installation of primary conditioning systems at the sample tap typically allows for more reliable operation of extremely difficult samples that cannot be transported easily to a remote sample conditioning system. Pyrolysis furnace effluents, regenerator gas from fluid catalytic cracking unit or FCCU, and reformers. Other hot gases with condensable material, particulate matter, and catalyst fines are examples requiring primary sample conditioning in order to maintain a reliable continuous sample draw-off without plugging. What is the Advanced Reflux Sampler? The Advanced Reflux Sampler is a filter reflux column that is mounted directly on the process line shutoff valve. The sample is cooled, and the condensable material reflux washes down the solids back into the process line, with a clean saturated sample coming out of the top of the column to the analyzer. Let us divide the Advanced Reflux Sampler into sections and understand the function and the operation of each section. First is the filter section. The filter section is the lower section of the Advanced Reflux Sampler. Its function is mainly particulate filtration and it provides some primary sample cooling. Typically flange mounted directly to the process isolation valve and flange mounted to the heat exchanger section of the Advanced Reflux Sampler. The filter media is nominally stainless steel wire mesh that traps any particulate matter such as coke from the ethylene furnaces and/or catalyst fines. During normal operation, the temperature at the filter section outlet should be in the order of 50 degrees Celsius, indicating a balanced refluxing condition is established. This filter section is cooled by the condensate that has dropped out from the heat exchanger mounted directly above the filter. The condensate also acts as a trap for finer particulate matter. In certain environmental conditions where sub-zero temperatures are anticipated, it may be desirable to insulate the filter section. This will prevent premature condensing and allow for a balanced refluxing action. From experience, the refluxed material may stuck and clog the process isolation valve beneath the reflux sampler. In this case, the filter section will be filled with condensate and the temperature in the heat exchanger section inlet will drop to ambient temperature. In this case, it is recommended to remove the Advanced Reflux Sampler and clean the process isolation valve during shutdown periods. Steam supplement. For the Advanced Reflux Sampler to function reliably, there must be sufficient quantity of condensable media in the sample. For applications that have high particle loading and limited condensable present, steam should be added at the inlet. The Advanced Reflux Sampler filter section has a steam inlet facility located at the inlet. A suitably rated needle valve is provided for regulating a nominal flow of steam into the filter section via an inverted tube such that the steam is directed up into the filters. Note that the steam is added directly to the sample and therefore the composition will be affected the H2O addition. As each application has many different operating parameters, there are no specific settings for the quantity of steam addition and each application is set up individually. Inlet temperature section. Mounted between the filter and heat exchanger section is the inlet temperature thermowell. As standard, a suitable temperature gauge is installed in the thermowell. The purpose of temperature measurement at this point in the Advanced Reflux Sampler is to help establish the correct temperature gradient required for refluxing. The two undesirable conditions within the filter section are as below. Temperature reading too high will cause the heat exchanger to work excessively and indicates a problem elsewhere in the system. Temperature reading too low will cause the condensable media to drop out early in the filter section and not provide proper filter cleansing by reflux. Heat exchanger section. This section provides the cooling of the sample and is most critical to the overall operation. As the sample gas rises from the filter section through the inlet temperature section, it is channeled into the heat exchanger chamber. The sample gas rises through a chamber in which the cooling coils are concentrically mounted. The design of the heat exchanger is such that maximum surface area contact between the cooling coils and the sample gas is achieved. There are two cooling coils located in the same heat exchanger chamber, which helps provide more accurate and efficient cooling. In the headspace of the heat exchanger, a stainless steel fine filter mesh is installed to act as a mist trap and final liquid sample droplet trap prior to exiting the sampler. Flow of the cooling media through each coil is automatically controlled to ensure a constant outlet temperature is maintained. The sample is normally saturated at the outlet temperature and pressure. The cooling media is supplied by Vortex Air Cooler via the self-acting controller. Finally, we will understand the vortex cooler theory of operation. Vortex tubes are simple devices that contain no moving parts and therefore may be used as a reliable device for generating a cold air supply. Compressed air, clean, dry, ISA grade, will enter the cylindrical chamber, to the left of the diagram, and is caused to rotate internally. This rotating air moves up the inner walls of the hot air exhaust chamber at extremely high velocity. When exiting the hot exhaust, to the top of the diagram, a portion of the air is directed back through the center at lower speed than the exiting air. Heat transfer from the inner slow-moving air to the exiting fast-moving air causes cold air to be generated. This cold air exits via the cold air exhaust, shown at the bottom of the diagram.